I'm Harriet. I'm a junior dev at SoundStacks, which is part of the Native Instruments group. So you may have heard of Native Instruments, hopefully, or Isotope, or Brainworks, or Plugin Alliance. That's all part of one big umbrella group. I've been working on the Cmajor platform for about 15 months or so, alongside Jules, Chairs, and Lucas. I'm a graduate at the Digital Audio Programming Masters over at the University of West London, and I've been interested in machine learning for years now. I started doing it in my undergrad days at Plymouth Uni as well. But obviously, everyone will know me from my defining work, which came from last night when my team came second in the ADC quiz. So big shout out to my team there. So, post-ADC last year, we sort of had our sort of ADC debrief where we sort of talked about what happened, what we liked, what was new. And we were like, what can we do? What can we do over the next year? What can we do for ADC next year? And what can we make? What's our goals? What we'd like to get done with Cmajor? Because obviously we are not at V1 yet, so we can still break things, which is nice. And what we were really keen on was getting some more tooling into Cmajor. So not only is our platform fun and useful and great, but working with the platform was easier and it's more useful than the go-to, hopefully soon, for audio DSP developers. And this is what started this talk and this work, basically. I mentioned to Jules and Chaz that, I'm interested in learning about machine learning a bit more. I want to know how inference works. I want to know what happens behind the scenes, what inference engine actually does. And there's so much tooling out there for inference. And the designers of the inference engines do some amazing work. And they make it as accessible as possible for as many people as possible. So for those of you who don't know Cmajor, I will go into a bit more detail later, but it's our new platform for DSP development. It uses an LLVM JIT backend, making high-performant DSP. Code is sort of split into this sort of graphs and processor architecture, and we use nodes and connections topology to create connections there. We work on a sample-based architecture, and we're looking at future work to make block-based performance for FFTs and stuff like that. So here's my talk layout. I've also done a fun, huge QR code for all my slides and examples. I've not actually put the slides up yet, so that's a lie. We've got through bullet point 1. We've only got 1, 2, 3, 4, 5 more to go, so let's get through it. So I thought I'd start by defining what inference is for everyone. And obviously, when I started this talk, I wanted to know what ChatGPT had to say, because, how do you find out if your talk is safe from the future or not? By asking ChatGPT. And I mean, the first thing that I like about this is the fact that they start so happy to explain inference. I mean, sure, I'd be happy to explain machine learning inference. Like, what? Who says that? And the analogy is actually quite great, actually. I do enjoy it. It's like, imagine you have a smart assistant, like a virtual pet, that you've been teaching to recognize different types of fruits. So I don't know where the pet analogy came from with a fruit, but we'll go with it. You've shown it hundreds of pictures of apples, bananas, and oranges, and told it what each one is. Great. Now your smart assistant has learned from all those pictures and instructions. Great. So machine learning inference is using that smart assistant. So you've made your little pet. It can tell you if you've got a banana. Great, cool. Bye. So this is sort of my log line from this talk. Inference is the process of giving a machine learning model unseen data to output a value. This is like the next step from training a machine learning model with your Python tools such as TensorFlow or PyTorch. This may be seen as deployment of your machine learning model, and there are various tools which you can use to train and inference your model. So just a quick note on training so everyone's on the same sort of line here. Just so I can compare the two and we're all on the same page. So in the training phase, you'll typically create your machine learning model. You'll run the model with labeled data examples, and then you'll test and validate the model. From there, you'll generally iterate on parameters and model layers to get the most optimal layer for your use case. When you're designing and creating your model, you're defining the tensors or the arrays for each layer, and this can then be used during inference to shape the input and output data. And then putting that all together, that looks like this. So how does this all connect? So after training, a model is used with inference. So for an example, your typical audio dev might have written a model to emulate a specific guitar amplifier. I know there are loads of those around. They'll have picked that model based on their research. Hopefully they've gone and done some studious studying for that and not just typed out various layers into Python to see what happened, as I do. decided parameters such as input and output sizes for each layer, and created this using a training tool of some form. And then this model will have already been validated to say, oh, hey, this does exactly what we want it to do, and this is what we want. So then the model is then saved in a format that can be read by the inference engine of some form. These can be different formats, and they do vary from training model to training model. Just going to have a quick bit of water. So what will generally happen is that you'll have a set input shape for your inference based on your training, so you'll have to reshape any incoming data when you come into this input for the inference there. And you'll feed that into the inference engine, yeah. So you might be using, say, like the last 100 samples or inputs for your input stream, and you'll have to have like a buffer for this. And then you'll have your deployed model over on the right-hand side, and then your output might also be in a predetermined shape that will need implementing before you do the next stage of whatever it is you're doing. What's important is that the input-output shape of inference engines are predetermined and fixed. So when working in your code base, you'll need to correctly pass this data in and out. So how do these work? I've got some bullet points here of key concepts and sort of the steps. So you'll load the model, you'll pre-process your data, you'll run the inference, and you'll interpret your output. So you might fill an audio buffer of samples, pass in X amount of values to the model. And this might be done using an API or library of some form. And these will generally have their own methods for loading in models that you have to use your output to do with as you please. So I've come back to my previous little nice model there, and so this is all done via serialization. When a model's ready for inference, you'll sort of save it and serialize it into different representations, and you might actually recognize some of these file extensions here. So TF-Lite and ONNX are serialized using flat buffers and proto buffers, respectively. .pytorch.pt, that's that bottom one there. That uses the pickle, the Python object pickle, to serialize models. RTNeural runs a script. I will also explain all these libraries in a bit, guys, don't worry. They run a script to create a JSON file to save models and weights. And each of these serialization protocols come with pros and cons, but they're not so important because for our use case, we've already loaded in the model from memory before we inference. So we're not looking at speed, we're looking at comparisons here. So one final note before I look at all these tools is these topology graphs that you may have seen. So serialized models are expressed in the sort of graph sort of thing, and these sort of highlights the execution of various layers of the machine learning model. It also contains all your tensor details, input-output shapes, and things like that. You can think of like a layer in this sense as the highest level building block for your machine learning model. And this example here, we've got a linear relationship between layers, so it all goes all the way down. There's no sort of feedback loops or anything. But this might be different. This may be displayed differently depending on the choice of characteristics within a layer. And likewise, this may alter based on the method of serialization. So I think it's time we have a look at some of these tools. Just a side note, obviously we're talking about inference, but this might be some of the training tools that you've seen, sort of the TensorFlow, PyTorch, Keras world. Obviously Keras is incorporated into TensorFlow now these days and stuff, so that's that. And then there are like a million inference tools, and these are just some of the ones that I wanted to sort of look at today. I'm not going to talk about all of them, but there's some cool ones here. TensorFlow turns into TensorFlow Lite, which then turns into TensorFlow Micro, and they didn't have time to make a cool logo for that one, unfortunately. So I just had to use some text, but it does exist. And then we've got ONNX up in the top right, and then we've got RTNeural. So, and those are the three I'm going to look at today. I'm going to talk a bit about TensorFlow Lite, a little bit about ONNX, and a little bit about RTNeural, and what I like about all of them and what I want to do when I'm making my own inference engine. So, let's start with TF-Lite. By the way, don't worry about the code. I just needed something to put on the screen that made me look really smart. So TF-Lite is from Google. It's sort of their lighter TensorFlow inference engine. It supports less models than TensorFlow. It's aimed at inference on mobile and edge devices. I've just put some basic steps up here, yeah. So that's the C++ API. The idea here is that smaller models require less overhead, so you can have a smaller API to run things like this. TF-Lite can also call models from TensorFlow as required via a flex delegate as well. Okay, and this is ONNX. ONNX stands for Open Neural Network Exchange, not like the Pokemon. It's developed by Microsoft, and it supports models from PyTorch and TensorFlow/Keras by exporting them to their .ONNX serialized file format. The idea behind this is to create an easier workflow for training different training tools, and ONNX themselves sort of give the example that some team members might be more up-to-date with TensorFlow, other team members might actually be more up-to-date with PyTorch, and that's the reasoning to use the ONNX format, so we can bring that all together and serialize in one way. They have a few language APIs, such as Python and C++ to run inference. Machine learning models, implemented with ONNX are often referred to as an ONNX graph, and this is due to the nature of their implementation. So ONNX actually break down layers into mathematical functions or operations. So this is a brief example. This is a basic matrix multiplication, which, if you're writing this, maybe you don't need a machine learning model, but it looks nice on the slide. This is sort of their generic matrix multiply algorithm, and that's one of their operators. And this can come from, say, like a dense layer if input and output is the same size. But this gets complicated very quickly, and I don't expect anyone to read the next slide, but you get this architecture where you have multiple inputs from different parameters for a model, and then you've got multiple outputs here as well. Yeah, it's cool. So the tool I just used to show you those graphs is called Netron, and I just wanted to give a huge shout out to this open source project. It's an amazing tool. It supports so many different serialized models, and they have so much support, yeah. So just go and give them some love and go and have a look. And if you yourselves find that if you're reading like the text of a machine learning model and you can't follow it, sometimes like as a visual person, I like to see the graph, definitely go and check Netron out. Okay, so the last one I want to talk about before we move on to writing an inference engine is RTNeural. RTNeural, developed by Jatin Chowdhury, Chow DSP. The idea is that it's for real-time audio devs that might not be interested in everything that bigger inference engines might have to offer. They also want a C++ API that's suitable for audio generally. And what I mean by that is real-time safety, and I will go into more detail about that in a minute. The idea is to be as concise as possible with as little abstraction as possible. So RTNeural supports multiple backends such as Eigen, SIMD, and the C++ STL. And this is a nice little API for high-performance C++ for a C++ audio project, and I really like how they lay things out and stuff. So let's just have a quick look at the suitability for audio from these inference engines. And what I want to do quickly is just define what I'm looking for in these inference engines for real-time safety. So this is probably mentioned at maybe every ADC talk, and there are some amazing talks out there on it and stuff. I'm going to generally say that we're avoiding things such as things that take an unbounded amount of execution time when running a real-time process. I'm not going to spend too much time defining like each way an inference engine may or may not be real-time safe. I just want to give it a little bit of context. So we're looking for locks, memory allocation, or garbage collection, and we don't want to have to wait for external hardware, so we're not hearing any clicks or silence or anything like that. So can inference be ran in a real-time process using the libraries above? Drum roll, please. Ta-da! Yes and no. So here's a quick overview. I just want to give a huge shout out to my colleagues at Native Instruments and Isotope for helping me with this thing, because I would sort of bug them and they would tell me their experiences and stuff, and that's what we've come up with here. So we found that ONNX uses dynamic memory allocations, so they use studge function quite a lot, and it's not actually real-time safe. They use smart pointers and STL containers as well. Although I do believe some people do run real-time inference with ONNX, there is some ongoing work to make it properly real-time safe as well. TF-Lite is more of a question mark. It is technically real-time safe because after you've ran inference once, subsequent inferences are real-time safe. There are some allocations that do need to be changed, but I mean, for me personally, when I was wading through the TF-Lite library, I just found that layer of abstraction to actually look at what they're doing to an inference quite high. So it's quite hard to tell sometimes in what context it is. And obviously, by design, RTNeural is real-time safe. It's literally what it was designed to do. Okay, so after I did all this research, I decided, hey, wouldn't it be cool to do an inference engine in Cmajor? But your first question might be, but why? Why do that when you can use all these great libraries with like thousands and millions of pounds of money to spend? So here's just like some points here. So I found TF-Lite can be tricky, especially when there are layers missing and you have to pull in TensorFlow. Running inference via their C++ engine is like relatively painless too. And obviously they have a great large audience base and they've got an easy to implement inference. RTNeural has a good base as well, so what I want to take from RTNeural is being as agnostic to training as possible. So I really appreciate the fact that you don't have to subscribe to one type of training method. ONNX isn't real-time safe, but it's also training agnostic, and it's easy to find performance gains in smaller operations, so we can do some work there and some magic behind the scenes to make this work. So, Cmajor, briefly. I'm hoping some of you saw our announcement talk last year, or hopefully you came to my workshop on Monday. It's a C-styled language designed for DSP signal processing code. Our aims are to match/beat the performance of C/C++, be simple enough to learn, to entice people to use it, and also make code portable across processor architectures such as CPUs, GPUs, DSPs, TPUs, etc., etc. And we've also got tooling, so we can compile to WASM, CLAP, or JUICE projects. Okay, so this is our objective now. It's worth noting that we aren't actually trying to match anything that Microsoft, Meta, or Google can create. It just wouldn't be possible with that. I mean, there's only the 4 of us. We'll never be able to do it. What we're focusing on is obtaining the best possible performance for a small subset of layers for machine learning models that allow researchers, developers, and programmers to create, test, and deploy real-time safe models. So this is my checklist of initial requirements. Sorry, my throat is going. We're real-time safe. We want to be real-time safe. We sort of get that for free with Cmajor based on how it's written. We want to be training agnostic as much as possible. We don't want to tell people how they should make their models. Sorry, I need to take a break. Okay, back in the room. And what we want to do is target those small models, small matrices, and build up over time. This isn't something that's going to happen, you know, in the 6 months that I've been designing all this stuff. We want people to work with us, and we want to hear what is useful for audio developers. We need to plug into existing workflows, and we want, you know, generally good performance numbers. That would be quite nice and sort of required, really. So sorry. So this is what we came up with. There are now a few options to inference in Cmajor. What we saw a lot of at the start of the year was people making their own DIY custom inference engines, and that's sort of what Native Instruments started doing when they started using Cmajor, and it's in Guitar Rig now, so you can you've been using it without even knowing, which is great. And then we sort of focused on writing an RTNeural to Cmajor transpiler because we thought that was a great place to start, and if we can do what RTNeural are doing as a base, then that's great. And then the next step to this was starting our ONNX to Cmajor transpiler, so we can hopefully target things that ONNX can create. I just wanted to mention also that we do have a feature request to support introducing external processors. So this means that you can introduce external APIs from ONNX and stuff, because again, we don't want to tell people how they should run inference. And for this walkthrough, I'm going to use a real example from Guitar LSTM. It's a deep learning model for guitar/amp/pedal emulation using an LSTM with Carus. It's a real nice open source example. And I thought instead of showing you my noddy scripts, it might be nice to see something real. And all I've done to change it is to add a few lines of code to save the model in various formats, but everything else is how it was written. Please bear with me. Okay. So RTNeural to Cmajor. I'm going to focus mainly on the RTNeural to Cmajor, simply because we've actually finished our implementations here, but ONNX is an ongoing work in progress. The model input is looking for a JSON file to be converted, saved from the various RTNeural formatted weights. So these are the arguments that our sort of command line tool will take. You'll look at your model. You can specify where you want to output it, give it a fun, cool name, and by default we use float32, but if you need higher accuracy, you can flip that to float64. And this is what's spat out. I will show this on a little bit later and do a live code demo, woohoo. But this is sort of the architecture we're looking at. What we really liked about RTNeural was that you could see the layers in the sort of topology way, and you can see the conv, LSTM, and dance. And that's how it's sort of laid out. So what I'm going to show in my VS Code window is these 3 files. So this is what we output. We've got a model.cmajor, and that contains all our nodes and connections and the weights to describe the model. And then we've got RTNeural.cmajor, and this contains definitions of the RTNeural operators required by the model. It's just something to note as well if you've not worked with Cmajor. We glue all this together by using a .cmajor patch file. And this is sort of like a JSON-styled manifest file. And that's where you can describe the patch properties and contain links to other files in the patch and stuff like that. Okay, and just like the RTNeural to Cmajor script, the ONNX to Cmajor transpiles the given .ONNX files into Cmajor. Woohoo, surprising. Our work in ONNX is a lot more work in progress at the moment, so we've just scratched the surface of, like, because their operators are so powerful, they can do so much and target so much, it's just so much work to do. Performance comes out on the next stage of this. We want to do some proper benchmarking so people can actually go, oh, hey, we are genuinely faster. I could put up some noddy numbers today, but it wouldn't mean anything because I could, I'm obviously going to say that it runs faster than their C++ API. Yeah, and that's the next work. And this is what this sort of code looks like. And as you can see, the output is a lot less human readable. It's very similar to RTNeural in setup. We've got the same nodes, weights and connections, but it's, yeah. So part of the work we've been doing is trying to decide whether or not we should hide all this or even have it. But we kind of for now, we like looking at it and seeing what it's doing and stuff like that. So let's look at our RTNeural transpiler. This is going to go well. And now I can't see it at all on my screen, so this is going to go really well. I'm just going to increase the font size a little bit so you guys can see what's happening here. So this is the model.cmajor patch file I was talking about, and as you can see, it's the exact same as the screenshot I was just showing. We've got layer 1, layer 2, layer 3, layer 4, convolution, LSTM, and dense, and this is where the connections are. I've just added this so I can show you the model with and without this sort of fun guitar amp emulation. The emulation, by the way, is based on a tube screamer, Ibanez tube screamer, because of course it is. And then we've got hundreds and hundreds of weights in different float formats. I just save this file and do a hot reload. What I'm going to do actually is comment out this first. Comment this one out. And you also get to hear my really great guitar playing. Whoopee. Let's see if this is all set up. Okay, great. And as you can see, we've got a blank GUI because we've not actually set any annotations up to have any knobs or parameters. This specific model doesn't take in any parameters. Aha. This is a fun feature of our VS Code panel. Okay. Got some nice jazz. Some non-offensive background jazz for your Wednesday at ADC. I am available for hire. This is Say a Little Prayer, in case you're wondering. Maybe you can hear that now I said it. And this is it through an Ibanez tube screamer, which is, I'm sorry. Hey, sounds pretty good, right? Let's scroll down, you can see this is our input. We've got a lot of clipping happening here, but hey, it's not. Brilliant, so that also shows our hot reload, which is a nice segue. Okay, cool. So I just want to give you a quick overview of what my GitHub repo looks like here as well. So this is my patches here. We've also got the ONNX to Cmajor one, but if you try and run that, you'll get a not yet implemented assert. I'm very sorry, I will get around to it, I promise. Which is why I'm not showing it right now. And this is like my fork of guitar LSTM. And in that, if I just scroll along here, or not, maybe I shut it. I'll just go into it. This is going really well. Aha, there we go. The only reason I want to bring this up is to show you what I did to save the models in various formats. So I included this TensorFlow to ONNX library. Obviously imported the ONNX library, and this is Jatin's from model utils import save model. This is his sort of method of serialization, as I was talking about earlier. And this is all as written from the guitar LSTM repo. And all I did then was add 3 lines of code here to ONNX model, ONNX to convert from Keras, saved it as a fun name, and then saved it in the RTNeural JSON. So that's all you're looking at adding, and this is all we wanted to add to someone's workflow. So the idea here is to be as simple as possible, so researchers get it, devs get it. It's all one way. Now I'm going to drag this and get away from it. Goodbye, VS Code. Thank you for your work. So, quick summary of what we've looked at then. So we've looked at what's inference. I've looked at inference versus training a little bit. I've gone into common inference tools. We looked at some real-time safety of inference, and I showed you my custom inference engine in Cmajor with a brief example. So thank you so much for listening to me, guys. I'm sorry my throat keeps giving out. I want to give a big thanks to the Cmajor group, SoundStack's group. Jules and Ches have been great mentors over the past year to me, and I really appreciate their feedback and input on this work. The whole team at NI have been great, and also all my friends at Dynamic Cast who have listened to my talk proposal, 2-3 iterations of this talk, and have given some real great feedback. And they're all here today, which is really nice of them to come. So thank you so much, guys.
Thanks, that was a really great, clear talk. Can
Thank you.
Tell me a little more about how you trained that model?
No.
Oh.
Because it's not mine.
Oh, I see, right, okay.
I can give you like a basic, so they've got 10 minutes of a WAV file playing various great, cool guitar riffs, and then they've got an expected output. So what they've done is obviously put the same thing through their actual Tube Screamer pedal and gone, hey, sound like this. And through they had 3 different training times. They had like a real fast one, medium speed one, and then like a long one that took hours. And I can't even remember which one I ran. I just wanted an example. So that's sort of how they did that. But, okay.
Thank you. I'm just gonna bring the microphone here.
One question. I'm not sure if this has been answered and I just didn't get it, but this Cmajor interface to RTNeural, does it call RTNeural, the C++ library in the background?
No.
Or what
No.
is executed?
So we've got a Python script, and we basically got a dictionary in there that sort of looks. So we pass their JSON file in. So they serialize out to a JSON model, and then that's what they call to run inference. So what we've done is hijacked that JSON file, and we're just going through it the same way that they would go through it. So we would go, oh hey, look, we want a dense layer. We'll take that dense layer. We'll take the input shape. We'll take the weights, and we'll put it into Cmajor.
Yeah, but what does happens when the inference runs? Is the matrix?
Oh, it's all Cmajor. It's all
implemented.
Yeah, okay.
Cmajor.
I can show you actually.
Okay, so this was my
Yeah,
question.
sorry.
Yeah.
So that was what the second Cmajor file was. Good question. My apologies for not showing it sooner. So this is our sort of RTNeural implementations. It's a real long file. I'm not going to go all the way through it, but this is sort of our maths behind it, and we've got some testing going on in the background to make sure that it's the same as Jatin's implementations, and that's sort of what we've done. We sort of made our own Cmajor versions of it all.
Thank you.
Thank you so much. Hey, brilliant talk. Very, very interesting. Love it. One thing I've been wondering, since you mentioned floating point precision support for 64 and 32, I know that at least in the sort of research area, the pruning and quantizing layers is a big, big thing, and it's oftentimes very, very necessary, especially to run on constrained devices, to put it that way. Is there going to be support for even more, even harsher quantization of these layers?
That would be great. That would be, yeah, I would love to do that, but I just don't have the time yet. It's just me. Yeah, in answer to your question, I'd love to do that. We're not supporting any optimizations just yet. We thought if we just target inference for now, we could then build into that. Also, Cmajor doesn't have float 16 support and stuff.
Yeah.
But yeah,
cool.
It would be
Thank
great.
you so much.
Okay.
Back here. Thanks for the talk.
Hi.
You mentioned that RTNeural supports different backends, like the Eigen one, for example, and they have all different performance. Depending on the network, they are faster or slower. How is it compared to Cmajor? What backend do you use there, or is it also vectorization based?
Yeah. So we have our own sort of internal vectorization process. I can tell you from our experience, we've found we are comparable to RTNeural using the Eigen backend. We're sort of running similar performance numbers on all sort of architectures. We're faster in most cases, but we've got a bit of work to do on ARM, where it's sort of a few milliseconds slower than that. So it's getting comparable. I hope that answers your question. Yeah, sorry, I lost track. Thank you.
We have one online question.
Yeah.
Our online question is, thanks, can the engine handle VAE models too?
VAE models. I've not tried it, so probably not, no. But it will do in the future, I'm sure. Yeah. Any more?
Thank you. Are there any more questions from the audience here? Okay, no questions from the online audience? Yeah, please feel free to find Harriet later in the
I love
hallways.
talking about this stuff, guys, so
Yeah.
please come talk to me,
In
honestly.
case you have any more questions. So yeah, thank you very much, everybody, for being here. Thank you, Harriet, for the wonderful talk.
Thank you, Anna.
And for making sure we have more real-time safe inferencing engines to use. Much appreciated. Thank you very much.
Thank you, guys. Cheers.